Hi student, today I am going to talk about a contingency table analysis. I splitted this module into two. The first module I will talk about the descriptive part of the contingency table, and in the second module I'll talk about the inference part. For the first module I am going to I'll start with a test for proportion, and then I'll show you how to generate a different type of tables and how to convert a matrix format to a table format, and how to get a structured table and a three-dimensional table to a structured table. And then there is another function called X tabs that in a VCD package, that how to use the X tab to generate a very structured table, and from there how to get a chi-square value that also generate a chi-square value. And then finally we'll use a lot of examples to get an idea how those codes should be used here in R for generating different kind of contingency tables. In this module, we will mainly focus on the categorical data analysis. I'll start with very preliminary descriptive of the contingency table, and then finally, ends with different measures of associations and of the contingency tables. In the next module, I'll split the categorical data analysis into two modules. Mainly now I am discussing my discussion is on the module 1, where I'll first start with the proportion test, and that is very important for contingency table analysis. So the function probe.test will carry out test of hypothesis and produce confidence intervals in problems involving one or several proportions. In the example concerning opinion on abortion, there are 424 yes responses out of 950 subjects. Here is one way to use the probe.test to analyze this data. There is a function called probe.test, and where you can pass the number of success on n, that is 424, 950. 424 is the number of success and 950 is the total number of trials. So the results you can see here has been displayed. The one sample proportion test with continuity correction. So data is 424 out of 950, null probability is 0.5, and chi-square value is 10.738, degrees of freedom is 1, p-value is 0.001505, and you also can get the 95% confidence interval, that is here 0.41 to 0.47. and sample estimates of the proportion is 0.44. These are all details of information that you will get from probe.test function. The null hypothesis pi equals to 0.5 is tested against two-sided alternative pi not equals to 0.5. A 95% confidence interval for pi is calculated, that you have I already shown you, and pi, both the test and the confidence interval incorporate a continuity corrections. If you don't want continuity corrections, the options are there. You can say you don't need continuity correction. Any of these default can be changed. Not only continuity correction, all the default values that are there can be changed as per your need. For example, I'm just changing as p equals to 0.5, alternative is two-sided, confidence interval says 0.95, continuity correction is true. If say, then it is continuity correction would be, there would be continuity corrections, but if you pass continuity correction as false, then it won't do the continuity corrections. So results would be displayed without continuity correction. Next, a few slides, I'll focus on the exploratory part of the contingency table, especially how to construct the contingency table in R. So I'll say for how do we enter a two-way tables as a matrix, that suppose afterlife. This example is taken from that example of Agresti book. So the afterlife is, suppose, matrix C435. There are 4 elements of a vector, and that converted into 2 by 2 matrix by rho equals to true, and then you can give the name of the dimensions as dimension names after life equals to list. First one is for row and the second one for the column. So first list C female male, and for column I can write C yes no. And then name of the dimension of after light, I mean that you can write as names dimensions after life equals to C gender and belief. That means these are the labels. First we enter the labels of the factors, and the name of the factors are gender and belief. That has been assigned in this manner. So one can now this can give you a 2 by 2 contingency tables with proper labels. So calculating the total sample size in and the overall proportion Pij is easy. Say you can just divide the afterlife by the sum of afterlife. That will give you the proportion. To calculate the row and column total in I plus and in plus j, and the row and column proportion Pi plus and P plus j, one can use the apply or sweep functions. I mean, suppose you want the row total, so apply afterlife, the margin is 1, and the function you can say sum. That will give you the row total. Similarly, you can get the column total as apply afterlife is the data matrix, and then margin is 2 for column, and the function is sum. So that will give you the column total. Similarly, you can use the proportion in this manner. Just use the function sweep, say afterlife margin is 1, then divide by row total. So you can divide by row total. I mean, for function I'm using the front slash as this is the symbol that we use for division. So that way you can get the proportion too. To a table from a data frame, let's have a look at the arthritis data is available in case form in the VCD package. That the VCD package, if you don't have, you can install and load it. So arthritis data is one of the data included in the VCD package. So it has actually 4 columns or 4 parameters: the ID, treatment, sex, age, and improved. So this is the head of the arthritis data set. You can see data frame. So here is treatment ID, treatment, sex, age, and improved. Now we can make a table by treatment and sex. So we can make a 2 by 2 table. That can be done. Say tab equals to with arthritis data, arthritis, comma, table function we'll use here. The table, treatment, comma, sex. You can separately attach the data, arthritis data, and can use table treatment dot sex. As I have not attached the data, so I just use the function with. For further details of with function, you can get the help of with. The documentation that are available in R will help you how to use with. So it will give you the 2 by 2 contingency table, the treatment, the row wise. If you interested to keep something on row wise, then you have to enter the factor first in the table, and then you have to stratify it by the second factor that would be displayed in the column. So here treatment is the row and sex is the column. Enter frequencies in a matrix and assign dimensions giving the variable names and category labels. Note that by default matrix uses the elements supplied by columns in the result. Unless you specify by row equals to true, it will always take the column. So that's the default for matrix assignment. But if you want the row wise assignment, then you have to say by row equals to true. So here say job sat is one example, again 4 by 4 table from Agresti. So here is the matrix. The full matrix was passed through a vector within a matrix function, and then the dimensions have been specified as 4 and 2. So the dimensions of job name can be assigned as list. Income equals to say less than 15k, 15 to 25k, 25 to 40k, and greater than 40k. Whereas in the column names, the satisfaction equals to C, very D, little d, moderate S, and very S. So this way we can assign the satisfaction level. And if you can see, now if you display the job set data, then you can see there is a 4x4 tables, and properly assign the labels of the factors for both in row and both and in columns. Job set is a matrix, not an object of class like table, and so some functions are happier with tables than matrices. You can course it by using the as.table function. Just pass the matrix within as.table function, it will be converted into a table object, and then the functions that accept table objects can be easily used. For example, suppose job set is equals to as.table job set, and that will convert it into, now it has been converted to a table object. So str job set will tell you all the descriptives of all the details of the job set data that we have assigned. In table form, the values of the table factors are ordered by their position in the table. Thus, in the job set data, both income and satisfaction represents order factors, and positions of the values in the rows and columns reflects their order nature. Yet for analysis, there are times when you need numeric values for labels of order factors in a table, for example, to treat the factor as a quantitative variables. In such cases, you can simply reassign the dimension names or attribute of the table variables. For example, here we assign the numeric values to income as the middle of their range and treatment satisfaction as equally spaced integer score. Say, dimension job set $income equals to C 7.5, 20, 32.5, 40, and dimension job set satisfaction $satisfaction equals to 1 to 4. Now one can you can again print the job set, then you will see how the dimension names have been changed. There are situations where, particularly for display processes, you want to reorder the dimension of an in-way table or change the labels for the variables or labels. This is easy when the data are in table form, and this apperm function permutes the dimension and assign to the names of the dimension names change variable names and labels respectively. If you have a data frame, if you have a matrix of table, then you have to convert that into a table form object, and then you can apply this. For example, the UCB admission data, that available in Agresti, that apperm UCB admission, C2, 1, 3, and dimension names are say yes and no, and dimension name of UCB is sex, admit, and department, and that will rearrange the complete tables. Before you can just display first the UCB admissions, and then you see how it is done. Then you can understand what's the difference between UCB admission data and UCB after apperm. There is another function called structured table that also for three-way or large tables. The structured table function in VCD provides a convenient and flexible tabular display. The variables assigned to a rows and columns of a two-way display can be specified by a model formula. For example, say library VCD, and here I'm just printing the here I color, that is the data available there. So the here I color, if you can print it, then you can see actually it's a three-way array. So sex equals to male, then you will have here and I. 6 equals to, so the here and I, this two-way table stratified by gender. So this way you can see this data stored. But if you want a complete table, that structure table that we say, just use the structure function and pass the data here eye color data, and that will convert into this table, if you can see. So now it is very easy to present in a journal or in any report. So sometimes this is very useful functions to convert this type of data to a structure table. And structure table, you can also use the formula type structure. For example, structure here plus sex, then left side of the formula, and right side you can say I, and here color is the data set. Then you will see the data has been arranged in this format. So first hair color, then sex male, brown, sex male, then just other way around. That also you can construct. So there are a lot of examples must be there, so you just try and you will get different way of representing the data using this structure table. So table that I already used, that you can generate a frequency tables for factor tables using the table function, tables of proportions using prop.table function. So prop.table accept the table object actually, so you have to convert the data into a table object, and that can be passed through the prop.table function. And marginal frequency using margin.table. So here I'm showing some examples. Here say n equals to 500, and I just generated a data set, my data A, B and C in this manner, and then you will get my data as data.frame A, B, C. So there are 3 parameters. Now I can create a my table with my data table A and B, and that will be displayed as A and B like this one. And then if you want the margin my table 1, margin 1, that will give you the row wise, and margin 2, it will give you the marginal total of this data column wise. So with respect to B you will get here the margin dot table, my table, comma 2. And the probe dot table, if you just pass my table within the probe dot table, that will give you the proportion. And that proportion you should mention, if you need row wise proportion, you should pass the margin as 1, and if you need column wise proportion, then you should pass the margin as 2. So this, for the rest of the 2 example, if you can see probe dot table, my table, comma 1, and probe dot table, my table, comma 2. That will give you, the second one gives the column wise proportion, and first one gives the row wise proportion. Another very important function in VCD package is the X tabs, and the X tabs function allows you to create a cross tabulation of data using formula style input. This typically works with the case form data supplied in a data frame or a matrix. The results in a contingency table in array format whose dimensions are determined by the terms on the right side of the formula. So you can see that the data that we had, 3 data A, B and 3 parameters of the my data is A, B and C. So here I am just reporting the table in this manner, X tab, and then the left side of formula you don't need to write anything, and right side is A plus B plus C, and that will give you a my table, and that my table can be passed through F table to get a structure construction. So just pass the my table to F table, then it will give you a structure value. And even you can get the summary of my table. That summary, it will give you like this: the number of cases is 500, the number of factors 3, test of independence of all factors, the chi-square. So summary will give you the summary of the table, and along with the chi-square test of independence. If a variable is included on the left side of the formula, it is assumed to be a vector of frequencies. So suppose here is a library VCD extra one data set is GSS. So the DSS tab equals to say X tabs count, left side is the count and right side sex plus party, that data equals to GSS, and that will give you the sex is male, female, male, and party is dame, independent, and rep. So 2 by 3 contingency table would be displayed here, and if you just get the summary of the GSS tab and pass the GSS tab within summary, will give you the independent chi-square test of independence. Next, we'll learn how to collapse tables levels. Sometimes what happens, due to a very small frequencies of some levels, we may need to merge them or collapse them to make the data appropriate for chi-square test or any other statistical test. So it is not so difficult, it's very simple. I'll show you here. The related problem actually arises when we have a table or array, and some purposes we want to reduce the number of labels of some factors by summing some sets of frequencies. For example, we may have initially coded age in 10 years intervals and decided that either for analysis or display purpose we want to reduce age to a 20 years interval. The collapse table is a function that can be used, that is available in VCD extra package. I'm just using this example. So create 3-way table and collapse age from 10 years to 20 years intervals. First, we generate 2 by 6 by 3 tables of random counts from a Poisson distribution with mean of 100. So here is the data that I have generated, is data expand.3. So final data is this, count is this. So data is actually Shebang data counts. So now the T1 equals to X tab count, formula style we are taking. So left side is the counts and right side sex plus age plus educations, and it will give you the 3-way table in this format. Now collapse age to 20 years intervals and in education to 2 levels. In the arguments, levels of age and educations given same levels are summed in the resulting smaller table. Suppose in a collapse table, T1 is the table, then age, instead of the age has 4 levels, so we want to convert into 2. So first 2 you assign 10 to 29, 10 to 29. Second 2 you assign 30 to 49 and 30 to 49. And third, there are 6 levels. The last 2 you can write as 50 to 69, 50 to 69. Whereas in education you can just write less than higher, less than higher, and higher, and that will collapse the levels into 4 levels to 3 and 3 levels to 2. You can see the table, might give you much clear idea. I think these are the basic functions that are available in R, will be used to display more. Mainly I focused in this module to how to display the tables in a very structured way for a data analysis, and some functions that I already told that might give some test of independence, chi-square test of independence result, but we'll talk about this later in the next module. So we have seen that how to test for proportion in R, and then finally how to generate different tables, the 2 contingency table, 2 by 2 contingency table, K by L contingency tables, and then how to get a structured table from a 3-dimensional array, and then finally we learn how to merge 2 tables together. And my this after completion of this presentations, it is expected that you people able to generate different kind of contingency tables by on your own in our statistical software.